We are looking at 6-7 notes on investigating graphs of polynomial functions. So I'm going to go ahead and read this with you. The equations for polynomial functions are classified by their degree. So we are going to be focusing on looking at that. The graphs of these polynomial functions are also classified by the degree of the overall polynomial. So each graph based on its degree will have distinctive shape and characteristics. So we already know that this is linear, right? And it comes from f of x equals x because we're looking at that as a degree of 1. And if you remember the names, that is a linear function, right? Degree of 1 is linear, so we get that line. Now, if we have an x squared, this one is f of x equals x squared. Whoops. That is the idea that we have our quadratic, and we're going to get that U-shaped curve for that parabola. So x to the first is always going to give us a line. It could be steep, it could be a negative slope, but we're always going to have a line. And x squared is always going to give us that U-shaped curve, upward, downward, skinny, wide, but it's always going to be that distinctive parabola. Now, we're going to introduce more, but we've already seen these parent functions. Now, we're going to talk about a little bit further, and we're going to talk about end behaviors, as in where does this graph keep going, much like when we talked about domain and range. So the end behavior is a description of the values of the function as x approaches infinity, positive infinity. We normally just put the infinity symbol. It's understood it's positive. We're also going to talk about it affecting negative infinity, and that negative sign needs to be there, just like domain and range, interval notation idea. The degree and the leading coefficient of a polynomial determine its end behavior. It's helpful when you're graphing a polynomial function to know about the end behavior. So we already know, if you think about our quadratic, this is when a is positive. Remember that idea? The ax squared? The x squared means it's a parabola, and the positive makes it go upward. If it was a negative ax squared, we know the graph would go downward, and that's going to affect the end behaviors. So this is what we should be comfortable with, and if we weren't, we could always type the function in our graphing calculator and get a better idea of what's happening. So if you're looking at this, this is degree of 1, so we're going to have something like x to the first as the highest degree. A quadratic is going to have that degree of x to the second. Your cubic function is going to be x to the third. So we see that this jumps back and forth. And then if you look at the fourth degree, do you see you have a little bit of extra? So cubic goes in two different directions, much like linear, where a degree of 2 reminds me of a degree of 4 because they both go in the same direction. So do you notice that the odd end behaviors are opposites and the even end behaviors are the same, as in both of these values are increasing for y. And then in fifth degree, do you notice that it goes in two different directions again? So it seems like the odd degrees, they go in two opposite directions, but the even degrees will both go in the same direction up or the same direction down. Okay, quartic is your fourth degree, quintic is your fifth degree. So those are the names we already learned. We should be comfortable with those. Okay, so that was some information. Now we have some information to fill in on this page here. So we already know f of x equals x is the same as saying x to the first. So the degree of this polynomial is 1. And what is the name of this polynomial? It is linear. So we know that's a linear polynomial. Now, this is the parent function, the most basic. It cuts through the origin at 0, 0, and there's no change in the slope. So the leading coefficient is greater than 0. So if we have a positive x to the first, our graph is going to go upward like this. And if the leading coefficient is less than 0, that means it's like we have a negative x to the first, and we're going to have a negative slope, right? Rise and run, you drop 1, you go over 1. Now, if you have a degree of 3, notice we skipped the quadratic. Are you catching that? So we have x to the third. This is a degree of 3, and what is the name if it has a degree of 3? We already know it. It is cubic. Okay, your cubic function, if it's a positive x to the third, is going to come up. It's going to do that sort of move and curve through and go back up. So think about this. This would have a multiplicity of 3, wouldn't it? So remember the odd multiplicity, how it goes through the x-axis? So this one goes through, has a degree of 3. It curves when it goes through. So it connects to what we just learned. And if you have a negative in front of the x to the third, a negative coefficient, it's going to reverse and it's going to go downward, much like this did. okay? All right, if we have a degree of 5, so this is a degree of 5. These, again, are the parent functions, the most basic. We call this quintic. This is a quintic polynomial. And if you have a positive in front of the leading coefficient or the leading term, it is going to start low and come up. It's going to wrap back around and keep going. So again, it starts low in the bottom left and goes high to the top right. Same thing here. If we have a negative in front of the x to the 5th, it's going to start high, come back, and then end low from left to right. So do you see that all of these are sort of in that downward pattern? Because they have a negative, all of these that are positive are going in an upward pattern. Okay, what do you notice about the end behaviors? So as x approaches, this is positive infinity on all of these. Okay, x is going to the right, agreed? So as x goes to the right, as x goes to positive infinity, all of these are going up. So as x goes to positive infinity, y also goes to positive infinity. And that's true for all of these. In words, as x grows larger, y grows larger. Grows larger, y also grows larger. Now, as x is going to negative infinity, so as we go to the left, so here's my negative infinity. Going out the x-axis, my y values are doing what? On all of these, my y values are getting smaller. So y is approaching negative infinity. So for this, both x and y do the same thing. As x gets bigger, y gets bigger. As x gets smaller, y gets smaller. So as x gets smaller, oops, hopefully you can write smaller better than me, y gets smaller. Okay, now let's go to the ones where we have an odd degree, but also a negative sign. So all of these are odd degrees, but we talked about the positive x and then the negative value on the x with the leading coefficient. So as x is increasing, okay, well, here's my positive infinity. On all of these, what's happening? My y is decreasing. Now notice I'm talking about end behavior. I'm not talking about what happens in the middle. End behavior is what's going to keep happening. What's going to keep happening as x increases, y does what? Goes to negative infinity. So as x, as x decreases. No, I'm sorry, I was right. As x increases, I was back to the other side. As x increases, y decreases. Okay, so as x gets bigger, y is getting smaller. Now, as x goes to negative infinity, my graph is end behavior is going up. So we're not worried about everything in the middle, just what's going to keep happening. So as x approaches negative infinity, y approaches positive infinity. What's that mean? As x gets smaller, I'm having trouble being neat, y gets bigger. So just sort of in real quick, brief terms. Okay, so we're talking about odd degrees here in general. So I'm just going to make that real bold here. If the degree of the polynomial is odd and a is greater, then what happens? The end behavior matches. So if you have an odd power, the end behavior of x is the same as y. They both increase, they both decrease. If the degree of a polynomial is odd and a is less than 0, so if it's positive a value or a negative a value, then the graph reflects across the x-axis. Okay, do you see this, that this reflected? Do you see this idea that this flipped? Okay. And the end behavior is sort of like the opposite, okay? The end behavior switches. So what do I mean by that? As x goes to positive infinity, y goes to negative infinity, or vice versa, okay? So they are opposite there. All right, in order to determine all this, we're looking at the degree and we're looking at the value. Now, we have even functions. So this should be no guess as to what's happening here. We have x squared, so the degree is 2. And what will we name that if it's a degree of 2? Quadratic. I'm not able to write as fast as I'm thinking. Okay, so as we have this is going to be a positive x squared. My graph's going upward. So we'll talk about the behaviors here in a minute. As this grows down, it's because I had a negative a value. So we already knew this. So now we're just using this and saying, hey, it happens with other functions. Okay, this has a degree of 4. Remember, these are the parent functions. We haven't done anything to them, haven't added, subtracted, multiplied by anything. And we would call this quartic. Okay, so with that, this is the one where the end behaviors go in the same direction for y. So they both go up or they both go down. We're not worried about what's happening in between, but a 4th degree, this would be if you have a positive number with your 4th degree, and this would be if you had like a negative coefficient on your 4th degree. So as x increases on both of these, the y also goes to positive infinity. As x decreases or goes to negative infinity, the y increases. So y is going to positive infinity. So you have to sort of change what your brain sees. And now if you look at these, as x increases, okay, x is getting bigger over here. So as we go out the x-axis, the y value is going down. So y is going to be approaching negative infinity. Do you see that idea? As I move out here, this is going to keep going down, down, down. And as x approaches negative infinity, as I go to the left, my graph is also pushing down on both of these. So y is also going to negative infinity. So if you look at these, it doesn't matter what x is doing. The y is going either up or the y's are both going down. I know this is not exciting, but it's going to be a big part of your trig and your pre-calc and calculus. So this end behavior introduction is going to help you make things a little bit easier. All right, the degree of the polynomial is even. So if the degree of the polynomial is even, like 2, 4, 6, etc., and a is greater than 0, then the end behavior is increasing, okay? It's going in the same direction. So the end behavior will be that y is going to positive infinity for both of them. If the degree of the polynomial is even and it's less than 0, okay, the leading coefficient is less than 0, it's going to reflect across the x-axis, and the end behavior is also going to be going as y is getting to negative infinity. Okay, so everything's going to be decreasing for y. All right, so I feel like we already had this. If the degree of the polynomial is odd, okay, the end behavior points in opposite directions. So I already showed that, but now we're actually writing it down. So if you have that odd x to the first, we had a line going in opposite directions. If we had x to the third, we had a hyperbola, and again, it's going in opposite directions. So the y is going opposite directions. If the degree is even, like the ones we just did, whether it's upward or downward, or it is that quartic, and it flips, they point in the same direction. Now, again, if you ever got stuck with any of these things, you could put the function in your calculator and see what happens, and then start drawing your conclusions from there. Okay, so let's jump into this and think about what we have. Can I get rid of this? So looking at just the function and not looking at the graph, we want to identify the leading coefficient, the degree, and the end behaviors for x's and y's. So looking at this first one, how many terms are there? 1, 2, 3, 4. And it's in standard form. The highest power is 3. So that leading coefficient is -4. I'm going to write LC for leading coefficient. That's -4. Okay. The degree, well, the degree is 3. which we would call it what? If it's a degree of 3, what will we name that? Cubic. And we want to know the end behavior. Okay, so first of all, if Delta Math would ask you something, sometimes they ask for the leading term, and that was throwing people off. The leading term is negative 4x to the third. The leading coefficient is the number in front of that, and the degree comes from the power on that. So just throwing that out there. We know that it's cubic, so it is going to be an odd degree, and the value of a is less than 0. So these are our rules. It's an odd degree, and a is less than 0. Okay, an odd degree, the cubic would normally, if it's positive, it would go like this. If it's a positive x to the third, it would start low and it would end high. But we have a negative x to the third. It is going to start high and end low, because remember, they're going to be the opposites. So I did a quick sketch. I have no idea what this graph would really look like. I just did a quick sketch of what the parent function should look like. So let's talk about end behaviors. End behaviors. As x increases, as x goes to positive infinity, the arrow is an actual official thing that you'll see. So this is not just me writing an arrow like I did here. It's saying x goes towards positive infinity. What does the y do? All right, so as x is increasing, if you think about your graph, x is going over here, the y is decreasing. Oh, I just wrote y is decreasing twice. Okay, scribble everything out there. Okay, as x goes towards negative infinity, so as we go to the left towards negative infinity, the y is going up, so we'd say y is approaching positive infinity. So reaching or approaching, that's what that little arrow means. Okay, so we have answered our questions with a little bit of extra, but we have answered them. All right, look at part B. Now, this one has 1, 2, 3, 4 terms. It's in standard form, and the highest degree is 6. So what's my leading coefficient? 1. And we said the degree is 6. Now, I don't have a name for a 6th degree, so we would just say a 6th degree polynomial is how you would say that. Okay, we've only worried about names up to 5, which is quintic. So if it's above 5, you just say 6th degree. Now, let's talk about the end behavior. Well, let's remember, this is another odd degree. So that means it's going to go, the y's are going to go in opposite directions. And in this one, a is greater than 0. So if we just base this off the idea of x to the third, it is going to move like this. Now, I know this is, oh, I said x to the third. Does anyone want to yell at me? This is not an odd degree. What is it? It's an even degree. So let's base it off of x squared. I know that this is going to go in the same direction. All right, so I have here a degree of 6 because it's in standard form. So my leading coefficient is 1. My degree is 6. We just call it a 6th degree. We don't have a name for that we're worried about. We're going to talk about the end behaviors. Now, it is an even degree and a is greater than 1. I don't know what the degree of 6 looks like, but I do know it should behave the same end behaviors as a degree of 2. So that's what's nice. Even powers or even degrees will have the same end behavior where both of the y values are going to increase because a is positive. So as my x reaches positive infinity on an even degree with a positive leading coefficient, my y value is going to approach positive infinity. As my x value approaches negative infinity, I'm going to the left. My y value is still approaching positive infinity. Now, let's take a minute and let's graph this just to sort of see what happens and if we're correct. So we don't need to graph this, but just to sort of see what's going on here. I typed in the function in my y equals. I'm going to go to graph. If you're not getting a good graph of this, you can go to your zoom function and hit the 6 zoom standard. Now, we're missing parts of it. So you can see this graph is coming in high from the high part of the y's. It's coming in, it comes down. We're missing what it does way down here, but eventually it's going to come back up. So these are sort of the end behaviors here. And this is why we say it's very similar to x squared. So as x is increasing, the y is increasing. As x is going to negative infinity, the y is still increasing. Now, if you wanted to see what was happening here, you would have to zoom out. And I don't know that we could zoom out far enough to see the bottom of this graph. Let's see. I still might not have gone far enough. It just made the graph a lot smaller. But it's going to dip way down here, probably then move around and then come back up because it's 6 degrees. So I'm back to zoom 6. So again, we weren't worried about what was happening. We're worried about the end behaviors, which increase here and here. You could also go to your table and take a look at it. If I go to my table, second graph is your table, you can see when x is -4, you're at 11,000 plus. When x is 0, you're at -2, and then you can see it drops again. So you can see these numbers get really big. Just for 6, you're at -7,562. Okay, but we got the end behaviors. All right, so now let's jump to, I'm giving you a graph. So I'm giving you a graph. You tell me information about it. Okay. Identify whether function graph has an odd or even degree. So not actually asking for what the degree is. Is it odd or is it even? Well, look at the graph. The end behaviors go in opposite directions. Do you see that? Is that an odd or an even degree? That's an odd degree. It's an odd degree, and I'm going to remind you because
how many times it went through the x-axis.
That's going to tell us what the degree could be, but the end behaviors tell us an odd degree. So end behaviors are opposite. As in, you have, when I say opposite, not x and y, but y is decreasing and then y is increasing. Okay, I shouldn't say end behaviors are opposite. End behaviors are the same for x and y. The end behaviors for y. Let's edit that. End behaviors for y are opposite. Because as x decreases, and this is something else we need to talk about. Let's just talk about this real quick. End behavior. As x decreases, what does y do? As x goes left, y goes, well, down, right? So both x and y are going to negative infinity. As x goes to positive infinity, what's the y value doing? It's also going to positive infinity. Now, what's that mean? Well, that means that so it's an odd degree. And is the leading coefficient positive or negative? It's going to be a positive leading coefficient. Because the end behaviors for x in x is the same, and the end behaviors for x and y are the same here. So they both decrease and they both increase. So you start low and you go high. So we're really using the idea of basing this on x to the third. Say it again. Why doesn't it go to negative infinity?
Because it'll hit a number at some point, it'll come back up.
No, the end behavior, it will keep going down. It's not going to come back up. So this is the wrapping around, and then it's just, this is going to keep going down, and that's going to keep going up forever. Yep, it's just going to keep on going. Okay, odd or even degree. And how do you know?
Give me an even.
It is going to be an even degree. And how do we know? Well, the y value is going in the same direction. So end behavior of y is the same direction. So that's how I know it's an even degree. And then would it be a positive or a negative leading coefficient? My graph's going which way? Downward. So the leading coefficient would be negative. Negative leading coefficient. Oh, took the time to spell it out. All right, now I know we don't need to do this, but if you think about this, end behavior, as x goes to negative infinity, As x goes to the left, the y goes down. So it's going to negative infinity. As the x goes to positive infinity, as we go to the right, the y goes to negative infinity. So the y's have the same end behavior for both values of x. Okay, so that brings you to the back. And now this is where we're going to talk about turning points. So this is how we could figure out what degree it is. Okay, so we just sort of keep building here. And this is our last little chunk. So a turning point is where a graph changes from increasing to decreasing or decreasing to increasing. A turning point corresponds to a local maximum or local minimum. Now this is important. This is definitely a calculus idea. When you talk about a local, do you see that this peaks here? That's not the maximum. This graph's going to keep going up forever. Isn't there an arrow on this? So guys, could you actually tell me the maximum value of this graph? No, because it goes to positive infinity for y. This is called a local maximum, and this is called a local minimum. And you can see that. Local maximum is at negative 1, 6. So 6 is the local y value max, and the local minimum is at 3, negative 26. So y is negative 26 is a local minimum. Because this graph goes on forever, there truly is no minimum. There's going to be y values going down forever. Okay? This is a cubic function, and it's a degree of 3, and it has 2 turning points. So if you look, you come up, here's one turning point, the local max, you come back down, here's your next turning point, the local min, and it goes on forever. Okay, so this degree of 3 can be smashed. Like the basic degree of 3 looks like this. But you can see this has sort of been smashed because something's changed and it's multiplied by something, adding, subtracting. Okay. The degree of a polynomial function n has at most n minus 1 turning points. Okay, so you know how this is a degree of 3? Because 3 minus 1 is what? 2. And how many turning points were there? 2 turning points. So that's how we can determine the degree. So turning points and at most n x-intercepts. So how many intercepts do we have, guys? 1, 2, and 3. Now, why does it say at most? Because remember, a quadratic might just come and the vertex bounces off the top, so you might only have 1 x-intercept, or maybe there's no real solutions. So you can have, if the degree is 3, you can have 3 x-intercepts. If the degree is 4, you can have 4 x-intercepts, or what? Less. Turning points, though, will always be n minus 1. Okay. If the function has n distinct real roots, then exactly n minus 1 turning points and exactly n x-intercepts. Distinct real roots means we can see them and differentiate them. It's not the same root twice like a perfect square. You can use a graphing calculator to graph and estimate maximum and minimum values. Okay, remember, we're also talking about the local max and min. All right, we'll use the graphing calculator and the calc feature, which is trace, okay, to help us find the local min and max values. So we're going to go ahead and use the graphing calculator to do this problem. You can probably read that on your paper a little bit better. So go into your y equals. Make sure all these plots are off. I'm going to remind you, because this happened yesterday. If you go to second y equals, do you see how mine all say off? If one of them says on, you can either click on it and turn it off, or go down to option 4. It brings you to the home screen, and it's asking you, do you want the plots off? Give it the command, and it will say done. So I hit enter. So this is basically asking you, do you want this done? You have to hit enter, and it will say, okay, I did this. Your plot should be off, but just in case. All right, let's go into y equals, and we're going to enter our function 2x to the third minus 12x plus 6. All right, that's what my function looks like. I'm going to go ahead and hit graph just so I can see it. Okay, now if you look at this, it looks like the graph that we were just talking about. Doesn't it look really similar to this? Okay, so I'm guessing it's cubic, but let's talk about these things. It says we can go into window and zoom, so we can do any of these things to help us. We can go to that trace key. See the trace key? Hit trace, and we can sort of trace. So I could get an estimate of the intercept there. I could get an estimate, just an estimate is what I'm going to get, of the local minimum. And I could go up to the top and get an estimate of the local maximum. Okay? The other way to do that, just to throw this out there, hit second and the trace button. Do you see above the trace it says calculate? It says value, 0, minimum, maximum, intersection. So if I'm looking for an x-intercept, I would do the 0 because that's a 0. If I'm looking for that minimum value, I can hit minimum. And the calculator's going to ask me for something to the left of the point I want, so I hit enter. See how it gives me my line? I'm going to go to the right. And then the guess is just somewhere in the middle. We don't have to be perfect. We just have to be left and right of the point and hit enter. And it gave me a minimum. Now, it's probably still rounded, but it's about 1.41, and the y value is negative 5.31. That's the local minimum. If I want the local maximum, I'd have to hit trace and go up by arrowing left. But guys, it's gone. Like, I can't see it, but I see right here, my y's, it goes from increasing back to decreasing. If I want to see it, hit zoom, and I'm going to zoom out because I want to see the top of that graph. Now do you see the top of your graph? And I can trace it and get an estimate, or I could go into second calculate and look for the maximum. So if I do that, I arrow to the right, I arrow to or left and right and in the middle, and it gives me my maximum point. Now, if that's hard to see, I could go back to zoom and I can zoom in, and if my cursor's there, it's going to zoom in on here. Notice I lost the rest of my graph. But that shows me my local maximum. Okay. I can also, like I said, find the x and y intercepts if I really wanted to. I'm going to go back to zoom 6. I could find the y-intercept here. I could find what my, so look, I have 3 x-intercepts, so the highest degree would be 3. I had 2 turning points, so 3 minus 1 is 2. All right, so I already found the local max and min, so I'm going to just write it down. By tracing it, you can. So the local max is about, y is about 17.31, and the local min, y value, is about negative 5.31. Now, I didn't give the full ordered pair because the max or min comes from the y value, okay? So now we're going to do these two. I should know that I could have up to 3 x-intercepts, and I should have 2 turning points. So go ahead and graph this. I don't expect you to know the max or min without graphing it. Why is it local? Because there is no true max or min, it's just the turning points. So go to y equals. I'm going to just delete that and sort of, I'm just deleting what I don't want and changing over what I do. All right, I put the function in. I'm going to graph it. Again, if you want to, hit zoom, and 6 is your standard. We should already be there. And here is my cubic. Notice it has a positive leading coefficient, so it starts low and it goes high. The y's go in opposite directions. So we could do everything on here, end behaviors, all that. I'm just looking for the 2 turning points. I'm going to hit trace. This is going to be good enough today. Try to find where that top is. And I'm looking about like negative 1.93. If we went to second calculate, this is a local max. So go left, go right. Doesn't have to be perfect. And I got pretty much the same thing, negative 1.93. So what is this? The max? Local max. Y is approximately negative 1.93. And then find me the local min. So again, our trace was pretty accurate, but if you want to be more accurate, you could go the other way. I'm looking about negative 4. I think it says 87. Does your calculator agree with mine? Because I have something else written down. X to the third minus 2x minus 3. What do you have? Yeah. Oh, is that a 0? My eyes are really bad. You're right. It is a 0. I see it now. It's 0. Okay. So go ahead and put the second one in. So that should be negative 4.08. Or no, I have 07, but we should be close. We should be within a 10th or a 100th. Yes. Okay, so last part here, I've got it in the graphing calculator. I'm going to hit graph. This is a degree of 4. So it's an even. And here's what it looks like. So it almost looks like a quadratic, but it's a degree of 4. Here's the thing, though. There's no other dips. Like, I could zoom out on this just to get a better idea. Am I missing something? And if I zoom out, it's pretty much telling me what's happening. And if I hit table, I can see that it's just going to keep increasing. There's no change in this. Do you see how it just keeps getting bigger? So I'm not missing any part of the graph, and it keeps getting bigger as the x increases. So if we go back to our graph, we weren't missing anything. It looks like a quadratic, so there is no local max. So don't leave it blank. Local max, you would write none, or I guess you could write NA for non-applicable. There is no turning point that comes up, but there is a turning point at the bottom. So what is your local minimum? Yeah, and I'm going to say y equals -6. I don't think we had to approximate that, right? So again, this is the idea where you have a degree of 4, but there's only one turning point and only 2 x-intercepts. 4 would be the maximum x-intercepts, and 3 would be the maximum turning points. And it just happens that I only have one based on what happens here.